Hello, my dear, and let's start our lecture on hypersonic dynamics. Today we have lecture number 7, and the topic of today's lecture is hypersonic equivalence and principal and blast wave theory. So let's start from beginning. Let's return to the Euler equation given in our last lecture, namely equation from 1 to 6. So let us write these equations for an unsteady for two-dimensional flow in the YZ plane. Okay? But note that in our previous work, the x-axis is in the free stream direction, and hence the YZ plane is perpendicular to the free stream direction. Are you agree with me? Okay, nice. Because we are dealing with flow in the YZ plane only. In this case, U component equal 0. And yielding, we can get next equations you can see on the left part of this slide. Let us non-dimensionalize these equations as follows. And we can get these several equations we can see on the bottom part of left part of this slide. This is very simple, and I do not need to stop more precise beginning. Okay? In the preceding, rho infinity and speed infinity can be treated as a reference quantity. You might ask what physical meaning they have in terms of an unsteady two-dimensional flow in, namely, YZ plane. Indeed, there is no physical meaning necessary here. Both rho infinitive and v infinitive are just reference quantities. However, we will use these values as we have before, namely rho infinitive in some free stream density, and v infinity is some free stream velocity, right? In the x direction, okay? And their physical connection with the unsteady two-dimensional flow in our YZ plane will be made later. So we can become to the next 4 equations on the right part of this slide. And you can now compare it with the left part. So now our equation inside turn back to the same equation, right? And compare these two sets of equations. You should know that others send slightly different symbols. They are identical set of partial differential equations. On one hand, these equations are the hypersonic small disturbance equations, which govern the steady three-dimensional flow over a hypersonic slender body. On the other hand, these equations govern an unsteady two-dimensional flow. However, because the sets of equations for these two cases are identical, there obviously is an equivalence between these two types of flow. This is the mathematical justification for the hypersonic equivalence principle. which can be tracked by the highest one of researchers. Simply stated, we have the hypersonic equivalence principle. The steady hypersonic flow over a slender body is equivalent to an unsteady flow in one less space dimension. Furthermore, examining these two sets of equations, left and right side, further, know that the symbol of x tilde in this equation, all tildes, and t tilde are equivalent, and that we may say as the x average x over L, as the t tilde t times v infinitive over L. And thus, from this equation, we can get the bottom one, x proportional v infinitive times t. So, this equation is useful in the physical interpretation of the hypersonic equivalence principle, to be discussed a bit later. The preceding equivalence was established mathematically. It can be established on a physical basis as well. To see this, consider the sketch shown in next slide. This slide. Visualize a fixed YZ plane which perpendicular to the page, as illustrated by the vertical lines on the left. Okay, vertical lines on this. A hypersonic body moving at velocity v infinitive, it penetrates this plane. In this figure, the body is shown as a body of revolution. But in general, the body can have an arbitrary cross-section. The trace of the body and its shock wave on the YZ plane at 3 separate times is shown on the right of figure, on this slide. So, figure on this slide, we have in the YZ plane, the change in body shape looks like an expanding cylindrical piston moving at velocity v, w. Because of the hypersonic equivalence principle, the unsteady flow in the YZ plane at the right of this figure, shown at various times, time t, as supposed as t1, t2, and next, etc., gives the corresponding steady flow result in the YZ plane located at various corresponding values of when x equal x1, x2 equal x3, and so on. So all of these shown at the left, where x equal v infinitive 1t. Therefore, we see how the steady hypersonic flow over a body can be constructed from an unsteady flow in one less space dimension, as you can see on the right side of this case. In this case, we may ask the next question: what is the practical advantage of this equivalence? The answer lies in the fact that solutions of the unsteady one-dimensional flow driven by a moving flat space piston and the unsteady two-dimensional flow driven by a radially expanding circular piston. The case shown at the right part of this figure. All of these exist in the classical literature. The important point here is that a solution to the unsteady flow shown at the right of this figure, okay, and does indeed exist in the literature. And because of the hypersonic equivalence principle, this solution can be carried over directly to the hypersonic steady flow, as you can see on the left part of this slide. Moreover, solution to the classical unsteady flow problem existed before the advent of major interest in hypersonic aerodynamics, which beginning from 1950s, and therefore were waiting there in literature or other publications to be of help to hypersonic aerodynamicists when the time came. Further illustrate the hypersonic equivalence principle, consider a simpler case. For example, the flow over a two-dimensional airfoil with chord length c. Here you see on the bottom, chord length c. As the airfoil penetrates the fixed vertical plane, we have in this case fixed vertical slit, the body motion acts like an one-dimensional piston moving in the z direction. Z is the upward direction. Okay? This piston motion is shown in the ZT wave diagram at the right part of this figure. But note that as the airfoil passes through the vertical plane, the equivalent piston motion is first toward increasing Z, reaching a maximum Z corresponding to the maximum airfoil thickness, and then retreating toward decreasing Z. The resulting unsteady shock and Mach waves are shown in the ZT wave diagram on the right side of this slide. These waves are directly equivalent to the steady shock and Mach waves over the airfoil on the left side of this figure. So where again we have x as equal v1 t as before, the known classical solution of the unsteady one-dimensional flow we can get on the right and can be carried over directly to construct the steady two-dimensional flow we see on the left. Okay? So, but note that if the airfoil shape is given by this expression as a maximum and function from x of s, f times f from c, and then the equivalent piston motion is described by right side, z proportional z maximum times f and times times t over t naught. Here t is measured from the instant, the leading edge of the airfoil, contacts the vertical plane, and t naught is the duration of a piston motion. So t naught we may be described as a c over v infinity. Also, in the steady flow picture shown at the left, but 1 second, here on the left, okay? We have at the VWP, yes, we have the WP, as to be value of the vertical component of the flow velocity on the body surface, where the slope of the body is dz over dx. So the slope of the body, this is that expression, dz over dx. So we may rewrite this expression. Vp at the value of the vertical component of the flow velocity. through the equivalence principle, this is exactly the same as the flow velocity in the z direction, adjacent to the face of the piston in the unsteady flow picture. So we may rewrite this expression in this case. But here Wp, is a dz over dt. Because Ex is a proportional V infinity times t, we can get this expression name. So Vp, it's a V infinity times dz to dx, yes, now our component, and get us this V infinity to V infinity we can, right? We have a dz to dt, get us Vp, okay? Which is consistent with the equivalence principle. Namely, the piston velocity is the same as the vertical velocity of the body surface as seen from the fixed vertical plane penetrated by the body. If we divide this equation by the free stream speed of sound, alpha infinitive, we can get next expression, and which transform is very simple result, m infinity times the tangent of theta. Remember that theta is the local inclination angle of the surface, okay? For small theta, we may say as a, instead of tangent, simply that theta. Moreover, the order of theta maximum is on the order of z maximum over c, get us expression as a tau. From that, we can obtain net expression on the bottom. WB over A infinity for maximum. It will be the same as WP over A infinity maximum and get us Mach number infinity times tau maximum, theta maximum, and this we get this expression of the O function. If we consider that maximum over C as a measure of the slenderness ratio of the effort, that is, we can get and remember that Z maximum over C is this tau. And we can rewrite our expression more simple. WB over A infinity for maximum, the same as WP over A infinity maximum. It's our function omicron from A. K is the M infinity theta, C times not theta, tau is the familiar hypersonic similarity parameter, right? So this last equation on the bottom indicates 2 points. First, the conditions for the hypersonic equivalence principle are the same as those for hypersonic similarity, which makes absolute sense considering that the hypersonic small disturbance equation are the basis for the both lines of dot. And second, the hypersonic similarity parameter we have K here, okay, can be given some physical significance on its own, and namely that it is on the same order as the maximum disturbance Mach number in the shock layer. You know, this has already been demonstrated for all practical purposes in our previous discussions involving K. I hope you remember. And the present development is simply a reinforcement. Okay, let's go. An important variation on the hypersonic equivalence principle is the application of blast wave theory. Returning to the right side of this figure, which we've seen recently, it's no new, but note that the unsteady shock wave motion and ensuing flow field are driven mechanically by an expanding system. A similar unsteady flow can be driven by the instantaneous release of energy at the origin, as sketched on the right side of this slide. Here, at the time when t equals 0, a large amount of energy is released at a point in the YZ plane. A strong cylindrical shock wave propagates from the point of energy release. It can be argued that the unsteady two-dimensional flow shown at the right of this figure is equivalent to the steady three-dimensional flow over a blunt nose slender body, where the blunt nose is blasting through the fixed vertical plane, provides the equivalent instantaneous energy release, which shown on the right. Results obtained from this equivalency are called blast wave results. Such results have been used to estimate the pressure distribution on axisymmetric blunt nose cylinders at hypersonic speed, with the cylindrical axis aligned in the direction of the flow as sketched on the left part of this slide. Blast wave results also being used to estimate the pressure distribution on two-dimensional slabs with blunt leading edges in hypersonic flow. Such a body is sketched on the left of this figure. Here, the blunt nose in blasting through the vertical YZ plane represents a concentrated line of energy release, which drives planar shock waves in both the upward and downward directions, as sketched, namely on the right part of this figure. The shock waves shown on the right of both previous figures and this one are called blast waves because they are created in both cases by the instantaneous release of large amount of energy, as would be the case of a concentrated explosion or simply blast, right? In this application, the blast wave results provide pressure distributions on the flat surface downstream of the blunt nose, as well as shock wave shapes in the same region. The pressure distribution and flow field in the nose region itself is quite another problem and is not provided by blast wave theory. In the blast wave analogy, the energy that is released is related to the wave drag of the nose, as follows. Now, consider the blunt nose flat plate shown in this figure. Let the D capital be the wave drag, so it have negative sign, okay, of the nose per unit span. The plate moves through a slab of air, which has thickness dx on this part, and in the direction of flight, and has unit length in the span y direction. drag is the force exerted on the body by the air. In turn, because of Newton's third law, the body exerts a force of the air in the equal and opposite direction, namely d. Yeah? And hence, the body does work on the air equal to d times dx. So d times dx, and because because of work is energy, right? Then the amount of energy per unit span deposited in the air is dE. And where we may rewrite as a dE, it's equal to d times dx. If you let the body move a unit distance in the x direction, then our equivalent from energy release get us very interesting and simple form. E from dimension from one unit get us d. Right? Very simple and nice. From this equivalent, we see that the nose drag is equal to E. In turn, from this figure, considering a unit span and a unit length in the x direction, we see that E is the energy released over a horizontal plane of unit area. That is, E is the energy released per unit area. In the one-dimensional unsteady blast wave problem sketched on the right of previous figure, we visualize that the line of energy release shown is an infinite sheet of energy release, where the sheet is perpendicular to the page. Okay? In turn, the blast wave in this picture are planar waves perpendicular to the page of infinite extent and propagating both upward and downward. And hence, in this picture, E represents the energy released per unit area of this sheet. And in turn, E equal D. E equal D, where D is the nose drag of the body per unit span. For the case of the blood nose cylindrical, as shown in this figure, the nose drag and the energy release are also related as well. Now, consider the axisymmetric cylinder moving in the x direction, as shown in this figure. The body moves through a cylindrical slab of air of thickness dx. From the same argument as just shown, the nose drag d of the body adds energy to this cylindrical slab, and equal dE equals d times dx. Thus, when the body moves a unit length in the x direction, the energy released to the air is E equal d from unit. It's simply d. Okay? So, once again, we see that the energy release is equal to the nose drag. However, here E is represent the energy release per unit length along the x-axis, in contrast to the energy release per unit area in the case of two-dimensional slab. Okay? Now, returning to the blunt nose cylinder as shown in this figure, we visualize that the blast at the origin shown at the right is in reality a blast concentrated along an infinite line perpendicular to the page, and that is the energy release per unit length along this line. The shock wave generated by its energy release is a cylindrical blast wave propagating outward in the radial direction and extending to an infinite extent perpendicular to the page. So, from the preceding argument, we have shown that the nose drag d is equal to the energy release per unit length d. Okay? So, generally, return to the previous figure and this one. The advantage of the blast wave analogy is that solutions to the unsteady blast wave problem, in our case, at the right side of the previous figure and this one, and can be found in the classical literature, and hence can be immediately transferred to the steady hypersonic flows shown on the left figure in this slide. As in our earlier discussion involving the unsteady piston problem, such blast wave solution can be obtained from the self-similar solutions involving ordinary differential equations. However, in the case of very intense explosion, where the pressure ahead of the blast wave can be neglected in comparison with the pressure behind the wave, analytic asymptotic formulas for velocity, density, and pressure near the center of explosion can be obtained. Of most interest to us is the pressure given in one research publication for the cylindrical blast wave in these various distinctive expressions. P proportional K1, rho infinity, and in parentheses E over rho infinity, square root from that, times T in power minus 1. Here, coefficient K1 you may find in these expressions. And for the planar blast wave, we can rewrite as the P in these more advanced form. So it's generally the same, but we have some changes the power in both coefficients. Here, coefficients K2 that preceded for beginning instead of K1 will be described in next expression here. The last two equations, as we can see, P and K2, gives the pressure near the center of the blast as a function of time t, with the energy release E, okay, with the energy release E as a parameter. In addition, let the coordinate of the shock wave be denoted by R as a radius. For the cylindrical blast wave, R is the radial coordinate of the wave, whereas for the planar blast wave, R is the vertical coordinate of the wave. From one research publication, we find that for cylindrical blast wave, we may write as these on the bottom expression: R proportional in parentheses E over R in rho infinitive in power 1 over 4 times square root from T. And for the planar blast wave, it's a bit the same coefficients, but a bit different power. 1 over 3 instead of 1 over 4, and T in power 2 over 3 instead of 1 over 2. Okay? Therefore, we can look upon this equation as solution for the flow shown as our picture. And let us now obtain the equivalent results for the steady hypersonic flows as we have in two previous figures. First, consider the cylindrical case, as you can see in this slide. And here in our equation, E is the energy released per unit length along the axis of the cylindrical shock wave. Okay? Hope you remember. As shown by previous equation, you remember that E equals D. Energy transformed into the drag. Because D is the nose drag, let us define a nose drag coefficient CD. In this case, we may rewrite as a CD as a drag over Q times F. Here's a Q infinitive, it's a 1 over 2 rho infinitive V infinitive square. And F as a pi D square over 4. And here we have as a rho infinitive and V infinitive are the free stream density and velocity respectively. Okay? For the body which we have on previous figure. And thus, from here, we can write that E equals D, or simply 1 over 2 rho infinity V infinity square times CD times pi D square over 4. And also, from the equivalent principle as embodied in previous equation, we can find that T proportional X over V infinity. Substituting last two expressions, here and here, we obtain expression from P. P chi rho K rho infinity square root from pi over A times V infinity D, and next square root from CD coefficient times V infinity over F. Recalling the perfect gas equation of state, namely P infinity proportional to rho infinity times RT infinity, the preceding equation can be written as you can see on the right bottom part of this expression. Pressure proportional coefficient K in numerator gamma P infinity, in denominator gamma rho T infinity, times square root from pi over A, and times V squared infinity, next coefficient square root from CT, in parentheses X over D, in power minus 1. So we have this expression as a pi. Recognizing that gamma RT infinity is speed of sound square, where A infinity is a free stream speed of sound, exactly, and noting that V infinity over A infinity is Mach infinity, the preceding equation becomes for gamma 1.4, namely for normal conditions atmospheric. We can write this expression P over P infinity get us this coefficient 0.8773 times K times M infinity square times square root from CD and times X over D in power minus. So we can become the blunt cylinder for this coefficient as 3 for P over P infinity get us coefficient K, exactly solution, times M infinity square times in numerator square root from CD, in denominator we have X over D. Inserting this equation into a previous slide, we have the expression for the right side. And or from here, we may found relating from R to D. It gets us pi over I in power 1 over 4 times coefficient CD in power 1 over 4 and times square root from xd. For a blunt cylinder, we can get this expression on the right bottom part of the slide. R over D, it gets us coefficient O dot 792 times CD in power 1 over 4 and times square root from X over D. Again, examining the left side equation, we know that the pressure distribution downstream of the nose of the blunt nose cylinder is given in previous expression as function of x. Yes, function of x. And this equation, together with next one, are blast wave result applied to the steady flow over the blunt nose cylinder via the hypersonic equivalence rate. Next, consider the planar case shown in this figure. And remember that in our equations, E is the energy released per unit area of the plane perpendicular to the page, okay? In this case, we remember that E equals D. For the blunt nose slab shown on the left of the figure, let us define a nose drag coefficient CD. CD is a D over Q infinitive times L, where, as before, Q infinitive is the 1 over 2 rho infinitive times V infinitive square. But now, as is a function from D of unit, 1 unit, get us simply D. And namely, the base area per unit span, okay? And thus, we can rewrite as E equals D, and it equals 1 over 2 rho infinity times V infinity times D times coefficient CD. Using this equation, along with the previous one, and for normal conditions, namely for gamma equal 1.4, the details are left. Imagine it's maybe your homework problem. That's very simple. As somebody who is interested. So for blunt slab, we may write these equations here. P over P infinity get us coefficients O dot 1 to 7 times M infinitive square times CD in power 2 over 3 times X over D in power minus 2 over 3. And the blunt slab get us equations, this one, R over D, its coefficient O dot 794 times CD over 1 over 3, very simple, that 1 minus this expression, and XD in coefficient opposite 2 over 3. Okay? How's mine? Examining the preceding results further, we know that the following for the blunt nose cylinder. First, the pressure distribution varies inversely with x. And second, the shock wave shape varies as x in power 1 over 2, square root from f. That is, it is a paraboloid shape, right? Also, the blunt nose slab, for the blunt nose slab, we know the following. The pressure distribution varies inversely as x in power 2 over 3. And the shock wave shape varies as simply x in power 2 over 3. Okay? Nice. So, also observe that P over P infinity for both cases varies with the square of the free stream Mach number, and that all of the results depend on the CD to some power. Recall again that CD is the nose drag coefficient, right? And we can estimate the values of CD from Newtonian theory. That's logically, okay? So specifically for hemi-cylindrical node, in our case, the blunt slab case, CD equals 4/3. And for a hemispherical node, in our case, the blunt nose cylindrical case, CD equals simply 1. Also, recall again that the preceding blast wave results are to be applied downstream of the nose of the body. Although x in the preceding equation is measured from the tip of the body. So blast wave theory cannot be applied to obtain detailed results on the nose itself. And this region must be analyzed by detailed numerical solution, such as was discussed in 2 lectures before, in lecture number 5. Okay? So, now we have next question. How accurate is blast wave theory as applied to hypersonic bodies? One of the most definitive answers for this is given by Lukashevich researcher, utilizing the blast wave results of Sakuri. Lukashevich compared theory with wind tunnel data for blunt nose flat plate and cylinder. Sakurai obtained 2 sets of blast wave results, identified as first and second approximation. The first approximation, which ignores the free stream pressure ahead of the blast wave, gives the results described in our equations we saw before. The second approximation takes into account a finite pressure ahead of the blast wave. These results, as applied by Lukashevich, are listed next. And note that the first approximation is the leading coefficient. So let's start from the blunt nose flat plate in our first approximation. We have two equations here in this, for P over P infinity and R over D. We just mentioned about both these equations. For blunt nose flat plate, for second approximation at the bottom, it's a bit more inconvenient expression, right? And blunt nose cylinder, the same for first approximation. I'm right here that you may compare it with that. We have difference in coefficients before, right? And some power in it, okay? Blunt nose cylinder in second approximation, we have analogically the same the coefficient different and the same power in this coefficient. So generally speaking, I maybe said that the coefficient x, it's a distance measured from the node in the flow direction. I hope you remember that CD coefficient is the wave drag coefficient of the node. D is a plate thickness or cylinder diameter. And R we're using here in this expression. So R is the value of Z at the shock wave. Okay? You know, Lukashevich compared the preceding equation with experimental data obtained at the Arnold Engineering Development Center, AEDC, Arnold Engineering Development Center, and with more exact theoretical results based on the method of characteristics. Some of these comparisons are shown in this figure. These and next step. In these figures, results are given for the pressure distribution over a flat plate with a cylindrical leading edge. But you should note that the first approximation compares more favorably with the wind tunnel data than the second approximation. However, as shown by the solid curve in this figure, solid curve, yeah? The second approximation can be brought into the close agreement with the data if the origin of the x-axis, namely the point at which x equals 0, is taken not at the nose of the body, but rather at the location 2/3 times d upstream the nose. Okay? In next figure, our previous data are plotted versus the blast analogy parameter. Blast analogy parameter x over d in power 2/3 divided by the m infinity square times cd in power 2/3, along with additional results obtained from the method of characteristics and also shown as the dashed line here is simple correlation of the method of characteristic result. So we may express in this equation p over p infinity as a coefficient times m infinity square times cd in power 2/3 and x there in negative minus 2/3 plus coefficient. For the theoretical result, the origin is again shifted by the amount of delta x. Delta x equals 2/3d. With the shift, the second approximation is seen to give good agreement with both wind tunnel data and the method of characteristics. Experimental, theoretical. Moreover, the result in this figure clearly shows that the trends which are predicted by blast wave theory are confirmed by experiment, and namely that for a blunt-nosed flat plate, in this case, the pressure distribution P over P infinity varies directly as M infinity and directly as CD in power 2/3 and inversely as X over D minus. Yes, results for shock wave shapes are shown in this slide, where the blast wave theory is compared with the exact method of characteristics. Clearly, the first approximation gives poorer agreement than the second approximation. And neither of the blast wave result is particularly good. However, our equations appears to predict the proper shape, but it is simply shifted from the exact result. If the results for both the first and second approximations are shifted upward by the amount of delta R equals D, much better agreement is obtained, as you may see in this figure. We have ideally lined up to the most part, and some part from the first and second approximation are a bit different. So the results from this tend to confirm that for a blunt-nosed flat plate, the shock wave shapes varies directly as CD in power 1/3, and directly as X/D in power 2/3. Right? Results for the pressure distribution over a hemisphere cylinder are shown in this slide. The first and second approximation blast wave results are obtained from both coefficients, and you can know that the best agreement with wind tunnel data at Mach equal 8, it's a bit more, 8.0.8, is obtained with the second approximation, with the origin shifted upstream of the node, delta x, as you remember, it's 1/2d, half d. Other data for higher M infinity plotted here in blue, and you can see as has very nice approximation with experiment. So we have all of these theoretical lines versus the blast analogy parameters. Analogy parameters X/D, M infinity, and CD. And here, the origin is shifted by the delta X, namely D. Once again, we see the general confirmation of the trend established in blast wave theory, namely that for a blunt nose cylinder, in this case, the pressure distribution P/P infinity varies. Directly, it depends from the M infinity, M square infinity, and directly as the CD, a square root from CD, right? And inversely from the X/D. The shock wave shape for a hemisphere cylinder is given in this slide. The blast wave results are compared with experimental data from Lees and Kubota, two researchers. Once again, we see that the shock wave location predicted by blast wave theory is not accurate. And you can see 3 line is not identical, okay? However, if the predicted shock wave is shifted by an amount delta R, as indicated in this figure, then good agreement is obtained. Moreover, this figure demonstrates that the blast wave theory predicts properly the following. We noted that the slope of the curve of the logarithmic plot is 1/2. And for the blunt nose cylinder, the shock wave shape varies depending the CD as 1/4, and directly with X/D, a square root from this of X/D. So, what I may say, a comment is in order now. The analogy between unsteady blast wave flow field and the steady hypersonic flow field over slender, blunt nose bodies is somewhat tenuous on physical ground, mainly because of the assumption in the classical blast wave solution of instantaneous energy release at a point or line in space. A hypersonic body does not add energy to the flow instant. And know this energy addition precisely at a point or a long flight. This is why better agreement is obtained in some of the previous plot by shifting the virtual origin of X. However, there is good physical reasoning behind the analogy between the steady flow of a hypersonic slender body and the unsteady flow in one less space dimension, the hypersonic equivalence principle. Because in the steady flow field, the disturbance velocity v prime and w prime perpendicular to the body axis, remember, are truly much larger than the disturbance velocity in the flow direction u stretch. You remember three components of speed, v, w, and u. In the final analysis, for whatever reason, blast wave theory does provide some relatively accurate prediction of the pressure distribution and shockwave shapes on blunt nose slender bodies, where the Reynolds number is high enough such that viscous interaction effects are negligible. Moreover, these blast wave results are in the form of analytic formulas, which are extremely handy for quick approximate estimate, an advantage not to be ignored, okay? And as a final note, the preceding result from blast wave theory can readily be expressed in terms of the pressure coefficient Cp. Cp will be approximately equal in upper part P minus P infinity in denoting 1 over 2 rho infinity V infinity square, or that keta 2 over gamma times M infinity square and parenthesis P over P infinity mass. So at a very high values of M infinity and P over the P infinity, so very high, many times higher than 1, and hence our equation can be approximately written in more simple form, in this case without 1. Cp proportional to 2 over gamma times M infinity squared times P over P infinity. Combining this equation with previous expression, and we have for our gamma equals 1.4, the blunt nose plate gets us this expression for Cp. And blast nose cylinder, the next one. As you can see, they have only different coefficients before, and Cd in power 2 over 3 and 1 over 2. And x over d in this here too. Okay? So you should note it that Cp is independent of M infinity. Blast wave theory is another example of Mach number independence at hypersonic speed. In one modern research, a combination of blast wave theory and straight Newtonian was used to predict the pressure distribution along the windward center line of the space shuttle. I hope you remember that that one shuttle. Yeah? Let L in our case, so that we use L, and denote the length of the shuttle. And the T, another expression here, is the thickness of the fuselage near the canopy. For the shuttle, the fineness ratio is L over D, get us 7. Moreover, the drag coefficient of a hemisphere from a straight Newtonian theory is when CD equal 1, and substituting these values, we can written expression for this one. Cp equal O dot 096 CD in power 1 over 2 times XL in power minus 1 and LD in power minus 1. And from here, we can obtain expression CP very simple. Coefficient 0.0137 divided by X over L. This equation called for 0-degree angle of attack. To take angular attack alpha into effect, let us simply add the Newtonian contribution for 2 sine square alpha, and we can get this expression here. Let us choose a point on the shuttle trajectory corresponding to alpha equals 40 degrees and Mach number 21 and 6. Which conditions mean? It's maybe returning from the moon. So our equation in this case get an expression Cp coefficient 0.0137 divided by the X over L and plus next coefficient here. From the results from this equation on the bottom are plotted on the card, and we can found that these results are compared with actual flight data from the STS-3 in open circles and STS-5 solid circles. It's all mission, space shuttle mission 3 and 5. And these flight data are obtained from open publication. The agreement between theory and flight data, we can see, and flight data as represented in this diagram is quite remarkable, especially when considering that the theoretical card can be calculated in a few minutes by hand. And this clearly demonstrates the value of both blast wave theory and Newtonian results. And this ends our discussion of blast wave theory and the general idea of the hypersonic equivalence principle. Our purpose has been to describe these ideas, to make them plausible on a physical and mathematical basis, and to show some practical results. Keep in mind that all of these results are limited to slender bodies at hypersonic speed. And in the next section, we will discuss a class of approximate inviscid flow theory that can be applied to blunt as well as to slender bodies. So, next question, thin shock layer theory. We have already discussed that shock layers over hypersonic bodies are thin. And as we see, remember from this picture, I hope you remember, in the limit as m became to infinity, 36 very high, gamma became to 1, we have shown that beta became to the theta. And in this case, the shock layer becomes infinitely thin and infinitely dense. In such a limit, we can consider the shock shape, the body shape, and the streamline shape is between to be all the same. Here we have 3 degrees difference, but in very high, practically, thin shock layer, very, very dense. Such approximation or variations of them are the basis of thin shock layer theory. In this module, the analysis developed by the Maslin will be outlined as an example of theory based on the assumption of a thin shock layer. Maslin's method is chosen here because of its simplicity and because of its frequent application, even today, for the approximate analysis of hypersonic inviscid shock layer. Moreover, Maslin's method gives results for the flow field over blunt as well as slender bodies, and therefore it makes a nice intellectual as well as chronological bridge between the recently discussed classical material in the model and the more modern computationally based blunt body solution. Consider now the curvilinear coordinate system as shown in this figure, where x here and y respectively are parallel and perpendicular to the shock, and u, look, and v are corresponding to the velocity. For simplicity, we will assume a two-dimensional flow. However, Maslin's method also applies to axisymmetric flow. Sorry. Now, assume that the shock layer is thin, and hence the streamlines are essentially parallel to the shock wave. In this case, in a streamline-based coordinate system, the momentum equation normal to a streamline, and we can rewrite as the upper equation on the right, rho times u squared over r. It's proportional dp over dl. Here, r is the local streamline radius, you can see here, of curvature. For the preceding assumption, our equation here becomes into the next one. How did we make this one? Rho u over rf over dp2y. What is difference? Rf. Rf is a shock radius over curvature. If I in a stream function psi, that's it, the rho u is a d psi over dy, and replace y in equation prior with our psi. Let's introduce a von Mises transformation, such as independent variables from x and psi rather than x and y. Okay? So in this case, we may rewrite now our next expression. Rho times u squared over rf. It's a function dp over d psi times rho u. Or we may rewrite in more simple expression. dp over d psi get us u over r sub f. Again, consider this a thin shock layer where all of the streamlines are essentially parallel to the shock. In this case, we may think as a u nearly as us. And in this case, the velocity just behind the shock, right? And thus, our equation on the left get us equation on the right. We have only different coefficients here in quantity. Integrating this equation between a point in the shock layer, where the value of the stream function is namely psi, okay? And just behind the shock wave where we have a psi is psi from S shock, we can get this final expression at the bottom. This final expression. This equation is the crux of Maslin's method. The flow fit solution progresses are followed. And first, assume a shock wave shape as shown in this figure. In this sense, Maslin's method is an inverse method, where a shock wave is assumed and the body that supports this shock is calculated. And hence, all flow quantities are known at point 1. As beginning, yes, psi at psi 1, point 1, And just behind the shock, we assume shock. And from the oblique shock relation, the value of psi equals psi1 and point 1 is known from expression we have from psi1 proportions rho infinity v infinity times h infinity, h1. So next, choose a value of C2. It must be between the positive values and less than psi1. And this identifies a point 2. Look at this figure inside the flow field along the y-axis. So here we have in point 2, we have psi2 equal psi equal psi2. The precise value of the physical coordinate y2 will be found in subsequent steps, right? Next, calculate the pressure at point 2, and we can get expression for P2. It's P1 plus U1 over R S times, in parentheses, psi2 minus psi1. Next, the entropy at point 2, entropy S2, is known because the streamline at this point 2 corresponding to psi equal psi2 and has come through the point on the shock wave. Let's say in shock wave point 2 prime, where in this we have in prime psi prime equal psi. So we may rewrite psi prime for this, for the same expression, rho infinity v infinity times h. Or we may found as the h2 get us expression psi2 divided by the rho infinity times v infinity. Therefore, h2 is obtained from this our equation, which locate our points 2 prime on the bottom here on the shock. In turn, the S2 prime is known from the oblique shock relation. And because of the flow is isentropic along any given streamline, we may say that S2 must be as the S2 prime. And finally, the entropy at point 2, in our case S2, is known because the streamline at the point 2 corresponding to psi equal psi2 and has come through that the point of the shock wave. And so we can see this from our expression here. As from psi2 prime or simply psi2, it's proportional to rho infinity v infinity times h. Or we may find h2 from this. Okay, first. Next, calculate the velocity at point 2 from the adiabatic energy equation in case when total enthalpy is constant. In this case, H naught enthalpy will be H infinity plus V infinity squared over 2. H naught is the total enthalpy, which is constant throughout the adiabatic flow field. Right? In turn, H naught will be proportional as the H2 plus U2 squared over 2. Here we ignoring V2. Or we may rewrite as U2 as square root from 2 times in parentheses H0 minus H2. All of the flow quantities are now known at our point 2. Referring to our previous figures and repeat the preceding steps for all points along the y-axis between the shock, in this case, I mean in point 1, and the body in point 3, the body surface is defined for the psi equal 0. So, next step, the physical coordinate y, which corresponds to a particular value of psi, can now be found by integrating the definition of the stream function, which is really the continuity equation, because d psi to dy is get us rho times u. And then we may find as y as integral between psi and psi s from d psi over rho. Here, rho and u are known as a function of psi from the preceding step. Okay? And this also locates the body coordinate y sub b as integral from 0 to p psi s. And this procedure is repeated for any desired number of points along the specified shock wave, and hence generating the flow field and body shape which supports that shock. Again, remember that the preceding assumed a two-dimensional flow only. Extension to an axisymmetric body is straightforward. Some results calculated by Maslin are shown in these two figures. In this figure, a paraboloidal shock is assumed, and the calculated body shape is shown. But note that Maslin's method is an inverse method, where the shock wave shape is assumed, and the body shape that supports the assumed shock, as well as the flow field between the shock and body, are calculated. Maslin's calculations of the body shape are shown as a triangle and are compared with more exact calculations. For example, the left side of this figure shows results in the nose region, which are compared with the exact numerical calculation by researchers for name one type. Excellent agreement is achieved. On the right side of this figure, results extending far downstream of the nose and shown. Here, Maslin's results are compared with the theories of Yakura and Sichov, based on hypersonic small disturbance theory and blast wave analysis. The corresponding surface pressure distribution in terms of P over P naught pressure. Yes? P naught here is the stagnation point pressure, right? And note that only a few points representing Maslin's results are shown. There is good reason for this. All of the results given by Maslin were calculated by him over the space of a few days using a hand calculator simply, which naturally limited the number of calculating points. However, this illustrates the practicality of Maslin's method, namely, that it is indeed simple enough to be carried out using a hand calculator in beginning of 80s previous century. The inverse method can be used in an iterative sum to calculate the flow over a given body. That is, the shock is assumed, and the supporting body shape is calculated. This body shape is compared with the given body, and new shock is assumed that will produce results closer to the given body. This iteration is repeated until the calculated body matches the given body closely enough. Using this approach, Maslin calculated the pressure distribution and shock shape for a hemisphere cylinder as shown in this figure. good agreement is obtained with the experimental data of Kubota, spherical. Also shown are the numerical results of Inouye and Lomax, based on the inverse blunt body solution, in our case, iterated, and the Misudov characteristic. Again, Maslin's method gives a reasonable result. Okay? Therefore, considering those three figures, Maslin's method, which is relatively straightforward to apply and can be considered an excellent example of general class of thin shock layer method. Also, note that Maslin's method applies to blunt as well as to slender body because of its accuracy and simplicity. And Maslin's method has found frequent application in inviscid hypersonic flow analysis, including up to the present day. Now, let's come to the summary. You know, hypersonic aerodynamics is highly nonlinear. Even the assumption of small perturbation, which in subsonic and supersonic flow leads to simple linear theory. And this does not yield a system of linear equations for hypersonic flow. Despite this, various approximate methods have been successfully developed for the analysis of inviscid hypersonic flow. We have discussed several of these methods in the present module. Some of them predicted upon the hypersonic small disturbance equation. In particular, the following is noted as first, the mathematical basis of hypersonic similarity rests upon this equation. From them, we have shown that flows over affinitely related bodies with the same values of gamma, m infinity tau, and alpha over tau. And that will have the same values of Cp over tau square, Cl over tau square, and Cd over tau cube. Here, Cl and Cd are reference to plane form area. Okay? So here we have as a m infinity tau is simply hypersonic similarity parameter. For a three-dimensional body, where base area is used as a reference for Cl and Cd, hypersonic similarity states that a finally related body with the same values of gamma, m infinity tau, and alpha over tau get us the same result. This because hypersonic similarity stems from the hypersonic small disturbance equation. And this concept applies only to slender bodies at small angle over time. The hypersonic small disturbance equations themselves can be directly solved for the flow field between the shock wave and body. In particular applications to Kuhn was used here to illustrate such a solution based on hypersonic small disturbance theory. Also, such solutions usually require a numerical treatment at some stage. The result can sometimes lead to closed-form analytical formula, such as are repeated next to the pressure coefficient on a slender cone at hypersonic speed. So we may rewrite as this expression, Cp over theta square over C, as expression here. This here was it. As well as the cone shock wave angle beta. In this case, k sub beta is dependent from k times square root from this expression. Here in the preceding k, it's a m infinity times theta t, and k sub beta, m infinity times simply beta. So the hypersonic small disturbance equation also lead to the hypersonic equivalence principle, which states that the steady hypersonic flow over a slender body is equivalent to an unsteady flow in one less space dimension. In corollary to this principle is blast wave theory, which allows the self-similar solutions to the unsteady flow field generated by an instantaneous release of energy along a line or plane, and to be carried over the steady flow downstream of the node of hypersonic blunt nose slender body. The results we can see here. Blunt nose flat plate in first approximation, we may be represented as this expression. Oh, as this approximation here. So it should be no second operation. It should be first approximation in power series. Blunt nose for the second approximation is a difference. We have get this coefficient and this coefficient. Blunt nose cylinder for first approximation may be rewrite of this expression. Blunt nose cylinder in second approximation, we may get next to expression. We should notice that for a blunt nose flat plate, the pressure distribution, in our case P over P infinity, downstream of the node and varies directly as m infinity squared, right? And coefficient CD square root from it. And inversely as x from d, in our case, x over d power 2 over 3. The shock wave shape varies directly as CD in power 1 over 3 and x over d 2 over 3. For a blunt nose cylinder, the pressure distribution P over P infinity downstream of the node, and we can there have varies directly is CD in power instead of 1 over 3, get power 1 over 4. X over D instead of 2 over 3, get a square root from x over D. Okay? So it is parabolic. Methods discussed in this lecture that are not predicted on the hypersonic small disturbance equation that and that therefore are not restricted to slender bodies at small angle of attack, high spot. The concept of Mach number independence. Here we observe both experimentally and from the governing Euler equation with the appropriate boundary conditions that certain non-dimensional aerodynamic quantities such as CL, CD, and CP and become relatively independent of Mach number above a sufficiently high value of. In our case, it's M infinity, which for blunt bodies can be low when we have Mach number 5. Second, thin shock layer method. These methods make use of approximations based on the thickness of hypersonic shock layer. As an example, Maslin's method is a straightforward application of the thin shock layer assumption and leading to a closed form equation for the variation of pressure across the shock layer. This variation represents as the expression at the bottom of this slide. It's a function P from X and psi, and get us three components Ps from X, this component, and a component on the parenthesis. This expression in turn allows the solution for all other flow variables within the shock layer. I hope this is enough for today. Okay, next lecture will be hypersonic investive force field. And for this moment, I may say classically, as usually I say for you, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue this lecture talk. Bye.